All right, guys. Today we are going to talk about emission spectra, and we're going to tie all these ideas of light and energy and wavelength all together today. So I want to do a little bit of a demo for you. So we're going to go back a little bit in our notes back before we did our light and wavelength and stuff. You should see this where we have a demo, emission spectra. Now I'm going to do this demo by sharing my laptop with you, and we're going to watch a YouTube video of one of my colleagues. He's going to put different tubes of gases that are elemental gases into an electric current, and we're going to let that electric current energize those gases, and we're going to look at the light that comes off of those gases. So the first one we're going to look at is hydrogen. Okay, so let me get this video up and we will watch this YouTube video.
We're going to look at the spectral lines created by excited hydrogen, helium, mercury, and neon. We're going to look at them through diffraction gradients. I'm going to try to place this over the lens of the camera. This one happens to be the atomic spectrum, or excuse me, the visible spectrum for hydrogen gas. You can see we have some nice sharp lines there. And as I do this, I'll rotate this for you so you guys can get a good view. Remember what those lines are. They represent electrons dropping from a higher energy to a lower energy. And when they do so, they give off a certain frequency or wavelength of light, which has a certain energy. And we can calculate the value of the energy levels in the hydrogen atom. Of course, Niels Bohr decided to use hydrogen first because it only had one electron to worry about. And he figured if he could find out what happened with one electron moving around the nucleus of an atom, he could extrapolate that to atoms with many electrons.
Okay, so when we look at this, I want you to see where we only see individual lines. We get this really bright red line up here, and we get this really bright blue line right here. So we, in the hydrogen spectrum, are seeing red and blue. So I want to go back to our notes here. What do we see in hydrogen? We see a red line and a blue line. Now, we really should see a few more. It's really hard to see the violet lines because they are really dark. They almost fade to the black. So let's look at this video some more. And next we're going to look and see what lines we see in helium. So we're going to go further on in this video.
That's hydrogen gas. I'm going to go ahead and switch this off quickly, and we're going to go to, I believe we have helium next. So switch that out for us.
Okay, so let's pay attention to what lines we get for helium.
Okay, so I'll turn that on. There's helium. And we'll do the same thing with our diffraction gradient. We'll place it over the lens of the camera. See if we can get a nice visible spectrum there. It looks pretty nice, doesn't it? So you can see we have a different set of lines for helium.
Okay, so let's look at these lines we get for helium. So we get a dark purple blue line, we get a light blue line, and we get a yellow line and a red line. So let's write those in our notes for helium. Okay, so let's go back to our notes. We get a red line, a yellow line, a light blue, and that kind of indigo to violet line. So I'm going to call it indigo because it's in between blue and purple. So indigo. Next, we're going to look at mercury. So we're going to take a look and see what mercury has to offer us. Okay.
Might be interesting to note that helium was first discovered not here on Earth, but on the sun. You guys can think about perhaps how that was done, maybe using a similar thought process as we're using today. Notice the spectral lines are different. signifying we have different values for the energy levels as the electrons are moving around the helium nucleus as opposed to hydrogen. So once again, that is helium. Okay, let's switch that out and we'll go to mercury vapor next. And we'll turn mercury vapor on. And we'll put our diffraction gradient over the lens. And boy, we certainly get a different spectrum there with mercury vapor, don't we?
Okay, so what do we see with mercury? We get a green line and we get an indigo line. So for mercury, we really only get green and kind of a bluish purple, indigo. So let's put that in our notes. So for mercury, we get a green line and an indigo line. I can't spell indigo. Okay. All right. And then we're going to look at neon last but not least. Okay. So here we go with neon.
So we have a lot of purples. You have that nice sharp green spectrum there, or that green color there that's visible. And all I'm doing is I'm rotating the diffraction gradient so you guys can get a good view of what's happening here. Okay, that's mercury vapor. Let's do one more. We'll go ahead and do neon next. Of course, that's everybody's favorite. So we'll put that in our... And we'll turn the neon on. And we'll go ahead and put our diffraction gradient over that, and we'll see, once again, a difference.
Okay, let's look at neon. We get a red line, orange, two orange lines, and kind of a yellow line. So that's why neon looks so orange when we look at neon signs, because it's all these warm colors. So we get red and some orange and some yellow. Okay, so let's put that in our notes. So for neon, we get red. Wow, this doesn't want to, right. We get red, we get orange, and we get two yellow, and it's kind of yellow-orange lines. Okay, so my next question is, were any of these spectra, did we get the same colors with any of these, the same combination of colors? No, we did not. So were any of these spectra identical? No, they were each unique. Okay, so let's take that idea a little bit further. Can I get spectrum for each of the different elements on the periodic table and actually have them each be unique? Yes, I can. So the big idea of these are emission spectra. Emission spectra are unique. And we can identify each element based on the emission spectra that we have. And they are used to identify elements. Okay, so this is how we identify the elements coming from stars. We know what makes up stars. This is how we identify what's in those nebula clouds when we look at the photographs from the Hubble telescope or any of the other telescopes. This is how astronomers figure out what the universe is made of. We look at the emission spectrum from the light coming from the various celestial bodies out there. Okay? And like Mr. Hummer said, helium was first discovered on the sun. It was not discovered on Earth. It was discovered on the sun because people were looking through these diffraction gradients, otherwise known as prisms to you, right? It diffracts that light into the rainbow. They were looking at diffraction gradients, and they were realizing that there was a spectrum coming from the sun that they hadn't ID'd here on Earth. And that's why they named it helium, because helium is named after the Greek god Helio, which is the god of the sun, Mercury, in the Roman vernacular. So helium, Helios, sun. Okay, so guys, let's skip down to where we're actually going to do some more work with emission spectrum. So here we are, a couple pages later. So this emission spectrum idea of getting very unique lines that correspond, and we now know that light, wavelength, and energy correspond to very different energies. So if I have different colors, like these emission spectra, I know have very different energies and very unique energies for each element. Okay? So Bohr pointed out that the absorption of light by hydrogen at these definite wavelengths, and hydrogen was always at very definite wavelengths, nothing else, correspond to definite energy changes in that electron. He reasoned that the orbits of electrons surrounding the nucleus must have a definite diameter to get those definite energies. So here is what Niels Bohr was thinking. If we have a nucleus in the middle, I am going to have particular orbits that go around that nucleus that give me different energy levels. So this would be energy level 1, this would be energy level 2, 3, and 4. And if I can get those electrons to jump back and forth between these different energy levels, I can get different wavelengths, because as energy is given off, photons are released. As we go down energy levels, photons are released, and some of these photons are in the visible light spectrum. And if I can see the visible light spectrum and use it to measure the different energies, I can use it to see what the energy is in between these different energy levels and know what those orbits are. Okay? So Bohr pictured the hydrogen atom as an electron circling a nucleus at a distance of about 53 picometers. He also imagined that this electron could absorb a quantum of energy to move to a higher orbit. So example, if I had, this is the same type of idea. If I had an electron here at energy level 1, and I gave that atom a bunch of energy, I sent in energy. If I put enough energy into this atom, I could give that electron enough energy to jump up to the next level. Kind of like jumping hoops or jumping to another rock. Okay? So if I could absorb some energy, I could move to a larger orbit, and the larger orbits have more energy. But stuff doesn't like to stay at high energy states all the time. Okay, could you imagine if you were running all the time? Isn't it a lot easier to just sit than it is to run? So, most things in the natural world like to stay at lower energy levels. So this electron that was bumped up is eventually going to fall back down. And as it falls back down, it is going to give off energy. Energy is going to come off of this. And sometimes that energy is in light that we can see, or visible light. Okay? When the electron drops from that larger orbit to the smaller one, energy is emitted in the form of a photon of visible light. Okay, the energy of this photon will be exactly the same amount of energy as we have between the orbitals. So electrons cannot be in between these energy levels. This can't happen. No electrons in between. They are either at an energy level or they're not. It's kind of like going up and down stairs. I can be on one stair or the other, but I can't float or levitate in between stairs. That doesn't work. Okay, I might have 1 foot on this stair and 1 foot on that stair, but my weight is going to be on one stair or the other. So I will really truly be on one step or the other. Okay, and when I go back down, I have to go back down to the stair. I can't float in between stairs. So these jumps of energy are just like going up and down on stairs. Okay, so now we get these very unique patterns for each element. And let's look at hydrogen again. So this is this is helium's. So when we look at helium, we get these lines right here. Okay, so this is helium spectrum. We get an indigo, some blue, some green, some yellow, and some red. Notice the energy absorbed also matches. These black lines are where the energy is absorbed, match the energy that's given off. So these on the top is the energy absorbed, and these visible light on the bottom is the energy given off as the electrons fall back down to a lower energy level. So energy given off is called an emission. Okay? So notice that the emission is the same exact energy as the energy that was absorbed to get those electrons to go and jump up to the higher energy level in the first place. Okay? So here's another way that we are going to look at this. So we have the ground state. This is the lowest energy level that an atom can have. Okay? And if I put in some energy to that atom, sometimes I will put in enough energy coming in that it will excite the electron. And if I give it enough energy, I can excite that electron to that next energy level up here. Eventually, though, all things want to be at a lower energy level. So if I can't stay at this excited state forever. So eventually that electron will go back down. And as that energy from the electron that goes back down is given off, so energy will be given off, or emission, and it will be the same amount of energy that it took to get it up to the top, up to the higher energy level. Okay, so energy in is going to be equal to energy out. Okay, so this is the Bohr model of the atom. And the visible series of this is what we call the Balmer series. And you'll notice that we show the 4 visible lines of the hydrogen spectrum that we should be able to see. A purple line, an indigo line, or a very dark blue line, a light blue line, and a red line. Those are the 4 lines that we should see on the hydrogen spectrum. We have an ultraviolet series, but our eyes can't see that. And we also have an infrared series as well. So we have a whole bunch of different energy jumps that we have the electron in the hydrogen atom doing as it gets excited to higher energy levels and then goes back down to lower energy levels. Okay? So the energy change is always the energy of the higher energy orbit minus the lower energy orbit. And that is equal to the energy of the photon. and that is equal to Planck's constant times the frequency of that wave that we get. Okay? Bohr's model explained hydrogen's observation of spectral lines. Okay? Just hydrogens. All the spectral lines from all the other different atoms, and we do get spectral lines from all the other different atoms, and we can identify elements based on their spectral lines. But those energy jumps for the other atoms did not match up to Bohr's model. Okay? The model failed to explain the spectrum of any other element. It only really worked for hydrogen. So if it didn't work for the other atoms, what does that mean we have to do? Do you remember on the scientific method? If it doesn't get supported by the evidence, that means we have to go back and rethink our thesis and change and tinker our thesis. So they had to rethink and tinker with the atomic model and come up with a different model and test that. Okay? So Bohr's model did not fully account for the chemical behavior of the electrons in the atoms. In fact, although Bohr's idea of quantized energy levels laid the groundwork for further atomic models, later experiments demonstrated that the Bohr model was fundamentally incorrect. So this is not the model that we currently use. The movements of electrons in atoms are not completely understood even now. So, however, substantial evidence indicates that electrons do not move around the nucleus in circular orbits. We actually have really funky energy levels and energy levels and shapes of electron orbits that are understood through quantum mechanics. And we're not going to get into quantum mechanics. Okay, so let's look at some of these things a little bit later, and we'll talk about how those spectra can help us ID atoms in the next video. We'll talk to you later. Have a great day. Bye.